Hello, everyone. Welcome to another in SNIA's networking storage presentations. This is all about NVMe over fabrics and the performance of different Ethernet-based transports. So today we have myself, Tom Friend, the moderator. Fred Zhang comes to us from Intel, and his background is in network devices, whereas both Eden Kim from Calypso and David Woolf from UNH have a deep background in storage lab testing. So we've got a great bit of very deep history and expertise in this. Before we begin, we first have to do the lawyer thing. Basically, what we're saying is we like it if you want to copy and use this stuff in your own presentations, but please just give us credit for it. And there's, you know, the engineer's take on what the lawyers have to say. So SNIA, which is the Storage Networking Industry Association, at a glance, we're 185 organizations across the industry, very much industry leaders. You know, you can take a look at the website. It'll give you a list of these companies. It's pretty amazing. We've got 2,000 plus active contributing members and more than 50,000 who keep track of us. So if you want to know more, there's the link on the page. And yeah. Technologies we cover inside the networking storage group include Ethernet, iSCSI, all these different things related to storage over a network. Today we'll begin with David Woolf giving us the introductions on this. He comes to us from the University of New Hampshire's Interoperability Laboratory. David?
Yeah, thank you very much, Tom. Yeah, I'm just going to cover a brief introduction about NVMe over fabrics. It's a relatively new technology, so we just want to talk about what it is, what its purpose is, and that's the part that I'm going to talk about here at the top, a recap of NVMe. And after that, I'll hand it over to Fred from Intel. He'll talk a little bit about some of the things that impact performance. But NVMe, what is it? A lot of us, of course, are very familiar with NVMe as a storage protocol for flash devices, for SSDs. And, you know, a lot of our laptops and desktops and many servers now use SSDs with a physical layer connection on PCIe and a protocol of NVMe that's optimized for talking to flash memory. So a lot of us are really familiar with, you know, an NVMe SSD, a single device that sits inside a laptop or a server or something like that. NVMe-of takes that protocol, which was specifically designed for talking to flash memory, which was optimized for talking to flash memory, and then maps it onto different fabric transports so that you can use that protocol, use that NVMe protocol across the network. So there's a few different transports that are supported by the NVMe over fabric specification today. We're going to focus on the ones that utilize Ethernet, so iWARP, RoCEv2, and TCP. That's where we're going to focus our presentation today, and we'll be comparing and contrasting those. So here, let's understand the differences between these NVMe transports, iWARP, RoCEv2, and TCP. What's the difference? And you know, tons of work and research has been put into comparing these. There's all kinds of resources online about this, a lot of materials from SNIA to help you understand the differences. This is just a very high-level overview to understand the difference between these three transports. So iWARP, a nice way to think about iWARP is RDMA over TCP. Memory access over TCP, memory access over the network. It's known for low latency, and because it uses TCP, it scales well on large networks because you get all of those benefits from TCP. You can increase your performance with iWARP when you use a TCP offload as opposed to having the TCP stacked in software. It does require iWARP capable adapters. RoCEv2, instead of being RDMA over TCP, it's RDMA over converged Ethernet. So we're kind of removing a layer there and implementing that in hardware. This too has low latency. It's really best suited for rack scale. So it doesn't have the same kind of scaling capability that you'll get with TCP. RoCEv2 also requires RoCE capable NICs and switches. They have to be able to decode the RoCE portion of the packets that are going back and forth. And we've got a little diagram there on the right that tries to explain that a little bit. You see that there's this InfiniBand transport, the RDMA access, or the RDMA verbs, if you will, the protocol there on top of the RoCEv2 stack. And that's on top of UDP, on top of IP, on top of Ethernet. And iWARP, you see it's a little bit different. There's an iWARP protocol. It's still DMA access, but instead of being on top of UDP, it's on top of TCP. So you can see some of the differences there. iWARP and RoCEv2 have been around for a long time. Of course, it's relatively recent that they've been used for NVMe-of, but those technologies are pretty well known. And you can see how that DMA access makes sense. It kind of lends itself to being used for NVMe-of because, again, we're talking to memory. And so a lot of those characteristics carry over very well to the iWARP protocol and the RoCEv2 protocol. The newest character in this cast of characters here is NVMe TCP. This is a protocol that was put together by the NVMe organization themselves. This is NVMe protocol mapped directly on TCP. So there's certainly some optimization that happens there. It's also low latency. Again, because it uses TCP, it scales very well to large networks. An important thing with NVMe over TCP is that it's easily supported using simple NICs and switches. And so, I mean, quite literally, if you've got a couple old PCs in your house and they've got Ethernet adapters on them, you can set up your own little NVMe TCP initiator and target network because you can use those kind of lower cost, less full-featured NICs and switches and still get a lot of the benefits of NVMe TCP. And again, of course, there, if you've got TCP offload, you can get some performance benefits there. So that's at a very high level, helping us understand what those different transports are and a little bit about the ins and outs of them. Again, there's lots of other material out there if you want to dig deeper on the differences there. So those are some Ethernet-based transports that are using NVMe-of. As we kind of alluded to at the beginning, NVMe-of is a relatively new technology. So if you're thinking of deploying it, if you're an early adopter and you want to be the guinea pig, chances are you're probably already using NVMe-of. If you're thinking about deploying it, a natural question is, well, how mature is this? Is this really ready? And so NVMe-of, they released their first spec back in 2016, and they released the 1.1 spec late last year, so almost coming up on a year now in 2019. So they've had some time to do some refinements to the spec, add some more features to the spec. One of those big features that got added between the 1.0 and the 1.1 spec was support for NVMe TCP. So the specification itself has been evolving and maturing. Another thing to note about NVMe-of is that there's been excellent driver support. From the very beginning, there's been Linux drivers available, both for initiator and target. So pretty easy to spin those up and get those working if you have the right adapters. More recently, there's been an NVMe-of Windows initiator produced by a company called Starwind. So we're seeing wider and wider support for drivers. That's going to enable adoption. Of course, testing. That's a subject that's near and dear to my heart. We've done a number of interoperability events at UNH-IOL, demonstrating interoperability amongst different NVMe-of products and on different transports. And also we have a series of conformance tests that we do to make sure that the NVMe protocol is followed, as well as the NVMe-of protocol. So lots of things going on. You know, the NVMe organization has really put a lot of priority on interoperability. So a lot of good things happening there. And all of that has led to this year, in 2020, lots of NVMe-of product launches. And so as this technology matures, as we see more products out there, naturally more people are thinking about deploying it. And that kind of leads to the key point of our presentation today is, well, what can be done to tune the performance of it? What's going to make sense for my workload and my network? And that's what our next section is going to talk about. So I'll hand it over now to Fred from Intel, and he'll talk about factors impacting different Ethernet transport performance.
Thank you, David.
Fred, let me break in for just a moment. Everyone, this is, in my hurry to get through the introduction, I left out a few important details for you. If you're new to BrightTalk, you should realize that if you put it in full screen mode, you'll get a much bigger view of what's going on this, in our presentations. Ask us your questions, and we'll answer them at the end, and if we don't have time there, we will have them up on our blog later. Give us your feedback as well when we're over. You know, we'd like to know how well we did. Was it worth your time? Was it truly awesome that you'd recommend to anyone else? Where do we fall in the middle? And for those of you who have been asking about the slides, on the bottom of your screen there's an attachments link. They're available right now. Go ahead, Fred.
Okay, thank you, Tom. Hello, everyone. This is Fred Zhang from Intel. I will talk about the factors that will impact the performance of NVMe Fabric. We're focusing on Ethernet-based transport for NVMe Fabric at this moment. If you look at the factors, there are multiple factors that will impact the performance of NVMe Fabric. On the host side, we are looking at
Okay, for the moment we've lost Fred. We're trying to get him back right now. Yep, in the meantime, you've seen the notes already about the slides being available. We have one question already from the audience, and the question is, what are the specific characteristics of RoCEv2 that restrict it to rack scale deployments? In other words, what's restricting it from larger scale deployments? It's a great question. Quite frustratingly, the person who could answer that best is Fred, and we've lost his audio for the moment.
So in the interest of covering for Fred on the slide, these are pretty high level comments, right? So the factors that impact NVMe over Fabric performance, we're focusing on the host side, which is the CPU, the drives, the switch settings are consistent, and the network are 3 different transports. So we're focusing on the RDMA-based RoCE and iWARP versus the non-offload TCP, and we're trying to normalize the drive and the host to focus on that performance delivery. We're using a single NIC card with a 100 gigabit Ethernet wire, and we will talk about other factors in future presentations, including the switch setup and multiple nodes and different topologies and congestion. So I hope Fred comes back. I'm going to forward the screen. Or can I? Yes. Did we go 2 slides? I believe we did. Let me go back one. Okay. So I'm still not Fred. This is Eden. So offload versus non-offload. As I said before, RDMA is the iWARP and RoCEv2, and IOs are offloaded so the host CPU is not used, whereas the TCP in this set of measurements was not offloaded. In the second bullet, as I said, TCP relies on the protocol stack and uses CPU cycles and affects performance as compared to an offload mode where the host CPU is not loaded or burdened by the transactions for the test IOs.
Eden, you'll need to continue. Fred got back to us, and he has a power outage where he's at.
Okay. So the next slide, there's quite a bit of latency here. Let me go back one. So for NVMe drives, they have different performance specifications, and they perform differently depending on the workload, whether it's read or write IOPs. There are a variety of drives with different performance factors, and in this case, the table there shows you 4 classes of SSDs and shows you the manufacturer specs in regards to read and write IOPs. However, when you actually put these drives into service, you get a different performance due to a variety of factors, which includes the application, the software stack, and all the components between storage and user space. But to take note, we are going to be doing both synthetic and real-world workloads. And you're probably all familiar with synthetic tests, which are the random 4K read-write or sequential 128K read-write single I/O streams. But in addition to that, we're going to be using some real-world workloads, which are a capture of application I/O activity during actual usage and is comprised of many different combinations of I/O stream patterns that change over time. So I'll talk about this more in my section, but one thing to note is that even when you use a real-world workload, there are many different types, and they can be heavy or light read-write. They can be read-dominant or write-dominant. They can have small or large I/O size and a variety of other factors that we'll see in the next section. MTU is the maximum transmission unit, and the standard frame is a 1500 byte frame, but we also have a jumbo frame, which is 9000 bytes. One of the things we're going to be doing is looking at the difference between these two, but in the context of the protocol, the maximum IP packet allowed without fragmentation is the standard 1500 byte. There are cases where you can use a jumbo frame, but when you use a jumbo frame, the target, the initiator, and everything between has to be tuned for that jumbo frame. And in addition, some OSs will force the frame to be 1500 bytes despite you wishing it to be 9000. Okay, I'd like to introduce Eden Kim. Eden Kim is a substitute teacher for Fred, and I hope, Fred, that I did justice to your section. Okay, so we're going to talk about test comparison of iWARP, RoCE, and TCP. So I urge you to go to full screen and also look at your download. The data is compact and the text here is small, but this slide just puts the context of the testing among the group. And basically it just says that we are trying to compare 3 transports, iWARP, RoCE, and TCP, and use a couple variables, one being the maximum transmission unit or the MTU regular or jumbo frame, 1500 byte or 9000 byte, and we're going to compare 2 types of storage. They are both 6-drive LUNs. One is called SSD1, and the other is called SSD2. SSD1 is a higher performance, lower capacity LUN, and SSD2 is a larger capacity, lower performance LUN. So when we did our test runs, we ran 4 types of tests, which you can see down below in red, and we ran them with one set of storage and changing the MTU variable and then comparing the 3 transports, and then we changed storage to the second type of storage and repeated comparing the MTU frames and the 3 transports. Some of the assumptions going into this testing were to look at, obviously, performance differences between the 3 transports. But in addition, there was a question as to will regular frame or large frame or jumbo frames show any difference in performance. And then, of course, underlying this is the storage. On the one hand, you have a higher performance storage, which is assumed to provide more I/O density so that you can get higher performance across the wire, versus a larger capacity, lower performance storage that may restrict or starve the wire and keep performance low because the storage cannot generate enough demand intensity. There's 4 tests we're going to run, but basically there are synthetic tests and real-world tests, and I'll go into more detail. But the first test is a synthetic corner case test, which is basically just running a random 4K read-write or a sequential 128K read-write, often known as corner case stress test. Then we're going to do a thread count QDEP sweep, which uses the real-world workload IO stream combinations to determine IO saturation as you turn up the demand intensity. I'll get into that more later as well. Then we have a replay test, which basically takes that real-world workload, which is a constantly changing combination of IO streams and QDEPs, and replays it against the storage. So you're having a dynamic replay of a bunch of different IO streams as opposed to a synthetic single IO stream. And then finally, we'll look at individual stream tests. We'll look at those 9 IO streams in the real-world workload and then test them each individually to see how each component of that real-world workload performs. So one caveat going forward, this is the first testing of these transports and storage, and the testing actually concluded late Sunday night. So we have the data and we can tell you what we saw, but we haven't spent a lot of time exploring why, and certainly we need to repeat the testing and we need to optimize the platforms. So you may see some data points that look weird due to anomalous conditions or due to other factors that need optimization. Okay, so looking at the test plan, objectives and setup, again, this is repeating, but the objectives compare the MTU, looking at IFs and quality of service. Quality of service means the response times at 5 nines. So 99,999 of 100,000 IOs are used. 1 IO per 100,000 is thrown out. We compare the transports. So the 2 RDMA offloads are iWARP and RoCE v2, and then we look at the TCP. And we look at this looking at a thread count QDEP sweep to look at demand intensity and saturation. Third, we compare a real-world workload looking at the replay test and the individual streams of that replay test. And then finally, we compare all of the above between the high performance and low performance SSD1 versus SSD2. In the larger picture, we have different performance platforms, but in this case, we're using only the high performance platform, which is defined as the CPU-based Intel 8280 at 2.7 gigahertz and a higher amount of RAM. There's a single high-performance NIC card on both the host and initiator across a 100 gigabit wire. There's no switch, and link flow control is on. As far as the test, so we're going to run synthetic and real-world workloads. To run the test, we put an asynchronous I/O stimulus generator on the host server to generate the I/O traffic across the wire to the target storage. And this is a Calypso CTS stimulus generator, which has been used in SNIA to develop the performance test specifications for SSDs and data center storage. The single I/O stream workloads of corner case, random 4K, sequential 128K, and the demand intensity is set at 4 threads and 32 queues for a total outstanding I/O. OIO stands for outstanding I/O of 128. On the other workloads, there's a different outstanding I/O. So on the replay test, it is comprised of the observed QDEPs, which range from 6 to 308. And on the thread count QDEP sweep, we run a combination of IOs from 1 to 576. And the purpose of these OIO settings is to set the demand intensity. So that's a knob where you can turn how high you want the demand intensity to be done to see if you are generating enough IOs to saturate the storage and or provide enough stimulus to the 100 gigabit wire to see if there's a performance difference. Okay, here is a image of the topology for the test plan. So you can see there's 4 sections on the left. That's your software operator, test operator, and that's a control server which has the test software and the database and the scripts. There is a IO stimulus generator, number 3, loaded on the host server. And we communicate from the test software database to the host server, and we send the workloads across to be applied to the logical storage that the host server sees. The host server looks to the target server and identifies the target storage as logical storage. There is a NIC on both sides between the host and the target server being on the right-hand side, and we run the 3 transports across the 100 gigabit Ethernet wire. The MTU settings are set so that it can either be transported using standard frame or jumbo frame, and once we apply the IOs across the wire, they are applied to either SSD1 or SSD2 as we set up. Each SSD is a LUN of 6 SSDs, again, SSD1 being the higher performance, lower capacity, and SSD2 being the lower performance, higher capacity. Okay, so let's look at the workloads and the tests. On this screen, there are 2 big charts. On the left, you have a representation of a real-world workload capture for a GPS NAS portal over 24 hours. Along the x-axis is the time, so it's 1440 minutes or 24 hours. And on the y-axis, you have IOs and IOPs. So the first thing to look at on the top is the queue depths. You can see the orange line varies between 7 and 368. So at different times during the capture, the demand intensity or the queue depths observed varied and peak at different activities. In the middle, you see the blue dots. So those are the IOPs, which are fairly consistent across the time. And at the bottom, you can see a bunch of colored columns. These are the IO streams. So we're looking at the 9 most frequently occurring IO streams that represent roughly 80% of all of the IOs. And over the course of time, they change in combination and amount. So at some times it may be all 9 IO streams, at other times a few. And you can see on that chart there are 4 spikes. In this case, each of those spikes are sequential half-K writes for 10,000 IOs versus the other IO streams that are occurring. So again, for this real-world workload, we have 9 IO streams, which was 78% of the total IO streams we observed. They're all writes, so this is 100% write workload. And on the replay test, we are just replaying the sequence and combination of IO streams and queue depths that we see here. On the right-hand side, we're taking those same 9 IO streams and averaging them across the entire capture. So in the green box on the right, you can see the 9 IO streams and the percentage of occurrence. We take that fixed composite, and for the thread count queue depth sweep, we apply those 9 IO streams and those percentages for each step of the test. And what we vary is the queue depth and thread count. So the thread count queue depth varies from 1 to 16, giving us a total range of an outstanding IO of 1 to 576. And when we measure the performance in terms of IOs, megabytes per second, and response times, these will vary depending on what the demand intensity is. So you'll see in later charts, the results of this thread count queue depth sweep will show you OIO on the bottom from 1 to 576 on the right, and then a megabytes per second or IOPS line increasing as you turn up the demand intensity, and then how the response times increase as you increase the queue depth and thread count. Okay, so let's look at some actual data. So the first thing we're going to look at here is comparing MTU, standard 1500 byte versus jumbo 9000 byte. And in this case, we're looking only at SSD1, which is a high performance LUN, and we're going to compare the three transports, iWARP, RoCEv2, and TCP. You probably can't see a lot of detail on this slide, but basically, if you look at the bars, the yellow bar is 1500 byte, and the green bar is 9000 byte, and those are IOPs. The circles are the response times. So the left-hand box is iWARP, the middle box is RoCEv2, and the right-hand box is TCP. So the first thing to observe is basically the IOPs, the bars, they're substantially equivalent for all the transports. You can see that the first two boxes, the RDMA-based iWARP and RoCE, are substantially similar in IOPs. There's a slight downtrend for the TCP on the right. The second thing to notice is that the response times in the circles are higher for the reads and in some cases for the larger block sequential 128K writes. So basically, when you look at the synthetic corner case, random 4K, sequential 128K, when comparing regular frame to jumbo frame, the IOPs are substantially the same, and the quality of service or response times are substantially the same. Another item to note is that for the RDMA-based testing, the CPU system usage was around 1%, and on the TCP, it was about 4%. So this substantial equivalence was then applied across all the workloads. So on this chart, and this is the only one you're going to see like this, it's complicated, but it gives you an idea. The left-hand side, green, is the test we just looked at, but in the chart form. It says random 4K sequential 128K read-write, and the performance is substantially the same. The lighter blue is comparing IOPs, and the darker blue is comparing the quality of service response time, and the red circles indicate where there is a high number or a deleterious value. In the next box, where it says thread count QDEF sweep, this shows you the second test, where we will show in more detail later, but here it just summarizes that they're substantially the same. And then the 9 IO streams individually measured from that real-world workload are each compared, and you can see that all of those are substantially the same, except in one case, the sequential 1.5K right IO stream is a little bit different. And then finally, for the replay test, where we replay the sequence and combination of all those changing IO streams, the performance between 1500 byte and 9K byte is almost exactly the same. I think somebody may need to go on mute. I don't know if that's you, Tom. There's a lot of background noise. Okay, so the conclusion is IOPs, there's generally no significant difference. And for quality of service or 5 nines response times, you get higher response times for some of the random 4K and sequential 128K reads. All right, so moving to the next test. Here we're going to compare transports. Let me get on the right slide. So in this case, we are looking at SSD1 again, and we're comparing the 3 transports. So each of those boxes are the 3 transports. Again, iWARP on the left, TCP on the right, and RoCE in the middle. And this is a test where we're running that fixed 9 IO stream combination that we saw previously for each step, and then we're turning up the demand intensity so that you can see on the x-axis the outstanding IO goes from 1 to 576. So for outstanding IO of 1, which is the lower left corner of each of these charts, thread count 1, QDEF 1. For OIO of 2, it's either thread 2 Q1 or thread 1 Q2. So there's 2 different values, they're averaged, so on and so forth. So by the time you get to 576, there's various combinations, but 16 times 16 is 576. So the y-axis on the left shows you response times, and this is on a log scale. So you can see that the purple line is 1 millisecond, which we place as the preferred maximum response time ceiling. The blue bars and red bars are response times. The blue bars are average response time, but what we're looking at as a figure of merit is the red bar, which is 5 nines or quality of service. So you can see as you turn up the demand intensity, you go from 1 to 576. The average response time and the quality of service, the blue bar and red bars, increase, but they generally stay below the purple line until a point to where you saturate the drive, and now the response times exceed that response time ceiling. So for most applications, IOPs and megabytes per second are easy. Response times are hard. I mean, if you don't get your request within your response time limit, you get a dropped value and, you know, it's lost record. So in this case, we can see that for iWARP, the green line is the megabytes per second. And as we turn up the demand intensity from 1 to 576, we go from 100 megabytes per second up to almost 3,000 megabytes per second. And it continues to increase on the right. If we were to go from 576 to 1,000, perhaps that green line would go from 3,000 to 3,500. But again, the figure of merit is quality of service response time. So the red bar you can see is at 1.1 milliseconds at 144 outstanding I/O. So there you have 2,700 megabytes per second at a 1.1 millisecond response time. If we go up from 144 to 576, we increase from 2,700 to 2,900. So we gain 200 megabytes per second. But the cost in response time is going from 1 millisecond to 4 milliseconds. So the application we're saying here doesn't like anything over 1 millisecond, so we want to pick the value before the knee of the curve, before the quality of service response times start to rise dramatically. If you look at the middle chart, it's the same thing. This is RoCE. So again, you can see as we turn up the demand intensity, the green line keeps going up, but the red bars exceed that 1 millisecond purple line at OIO 144, and the cost of going from OIO of 72 to 576 is 5 milliseconds, whereas we only gain 400 megabytes per second. Those two cases are RDMA and offloaded. On the right-hand side is TCP, where the host CPU is being used. And here you can see a dramatic difference in performance as well as response times. And we'll have a close-up of this later. But basically, you can see all the red bars are touching the ceiling and then go way over on the right-hand side. And from a megabytes per second of 2,300, it goes only to 2,900, but the response times increase from 1 millisecond to 60 milliseconds. So again, we'll go into this more detail, but the takeaway here is basically that when you turn up the outstanding IOs, you increase your megabytes per second on IOPs, but the cost is what's the response time. And since the figure of merit is response times, we want to pick the zone where we get all of our response times back in 5 nines, and we don't have dropped IOs. So in that case, for the RDMA-based transports, we look at around 72 to 144, and for the TCP, you can see that while we do get to 72, the IOPs are up and down, and the response times go very, very high on the right. Okay, let's look at an easier data slide. We're looking now at the replay test. So remember, the replay test takes those observed I/O streams across time, and they change for every step of the test. So there may be 740 data points or 720 data points. Each one has a different I/O stream content and a different IOPs and different response times. But for this replay test, we just average those all together. So for a simple look at those 9 I/O streams that occur in different combinations and at different QDEFs over the test, the average is shown in this plot. So again, iWARP and RoCEv2 are substantially the same, 122,000, 129,000 IOPs, and the 5 nines response times are 0.4 milliseconds. On the other hand, the TCP, you can see, is only 83,000 and doubles the response time to 0.8. So again, this is probably the difference between offload and non-offload. So next, we're going to look at those 9 I/O streams, but let's break them out and look at them individually. Okay, so we just looked at them as average altogether, but when we break them out and test them individually, we can see a lot of differences. So the left-hand box are the IOPs for each of those 9 I/O streams. Yellow is iWARP, green is RoCE, and then the TCP is orange. The right-hand side are the response times or quality of service. So obviously for IOPs, higher number is better. For response time, a lower number is better. So just looking at it, the blue circles show that the RDMA for most block sizes are higher than TCP, and they're substantially similar. On the right-hand side, looking at the response times, you see that the orange bars, which is TCP, are oftentimes much higher than the RDMA base. And if you look more closely at the block sizes, you can see that it might be for a particular block size, small or high or random or sequential, but clearly you can see that there are cases where TCP has a much lower performance for IOPs and much higher response time, such that when you mix them all together, those few I/O streams that TCP doesn't handle very well end up dragging down the overall replay test. So this real-world workload happens to have 3 or 4 very small, fragmented, random block sizes, which are difficult to manage. There are other workloads that have more reads and more traditional block sizes, which are easier to handle. So the storage may handle one real-world workload very well and another one very poorly. So again, the main point in the larger context is your performance really depends on the workload and the workload content. Okay, next slide. Here we are looking at comparing drives. So before it was all on drive 1, which was SSD1, which was the high performance, low capacity. Now we're going to look at, well, let's compare the SSD1 high performance, low capacity with the SSD2 low capacity, I'm sorry, high capacity, low performance. Okay, so again, iWARP, RoCE on the left and middle, TCP on the right. This is the case where we're looking at that 4-corner stress test, random 4K read-write, sequential 128K read-write, and then you can see which columns are in the red or what they are. But basically what you're seeing is that in all cases, the top row, which is SSD1, has higher or substantially equivalent IOPs compared to the second row, which is SSD2. And for example, in the very first column, 4K writes, 741,000 to 564,000 IOPs. And then you can see that the response times were only 0.38 milliseconds compared to 7.5 milliseconds. So a huge difference. In some cases, they're substantially similar, like the 128K read and the 128K write, 26,000 IOPs. And then you compare between RoCE and iWARP, they're substantially the same, and TCP is lower. Okay, the next slide we're going to look at now is looking at those demand intensity, thread count, QDEP sweeps, but here we're comparing drives. Okay, so on the left is SSD1, and the right is SSD2, and this is for iWARP at 1500 byte. So basically, one thing to note is this is log scale, and this is done so that we can see more clearly the megabytes per second and the response times not overlapping each other. So first looking at the line, the brownish line, you can see, as we saw before on SSD1, we went from 118 to 2,900 megabytes per second and kept going. But the response times passed 144, and that blue circle went up to 2 and 4 milliseconds. So at the optimal OIO 144, we had 2,700 megabytes at 1 millisecond. If we go to 576, we gained 200 megabytes per second, but it costs us 3 milliseconds of response time. On SSD2 on the right, we can see that first, the megabytes per second are substantially lower. Instead of going up to 2,000, we goes up to 600. Second, you can see that the bandwidth or megabytes per second is kind of a sawtooth, and you see low dip points at OIO 8, 16, 32, and 40. So there's a mismatch between the demand intensity and the available cores and other things that we can talk about later. But basically, the megabytes performance is lower and it's more sawtooth. look at the response times, you can clearly see the red bars are all above the 1 millisecond response time, regardless of where you are. And when you get out to the end, while you may have been, 12 to 20 milliseconds to 144, now you go to 30 and 40 milliseconds. So all things considered, the algorithm says, well, hey, 144, you're at 400 megabytes per second at 20 milliseconds. That's the best you're going to do, because when you go to 288 or 576, you go up to 37 and 48 milliseconds, which are dramatically higher than 20. So again, the figure of merit is response time, quality of service, and the algorithm measures the slope increase of those average QoS numbers and determines the need to be at 144 and 28 milliseconds compared to going up to 37 and 49. So this is iWARP. If we look at the next slide, we're going to be looking at RoCE, and it's going to look substantially similar. So here, with RoCE, again, you can see that for the SSD1 high performance, we go from 136 to 2900, almost 3000. The red bars stay below that 1 millisecond line nicely until you get to 288, 576. And the cost of adding 200 megabytes per second is going from a response time of 1.15 milliseconds to 5.5, which, from a algorithmic point of view is a steep increase, but from a practical point of view, your application may not care that 5 milliseconds is there. So the implication of this chart is that you should rerun the test and run the demand intensity up to maybe 1024 and see if that megabytes per second keeps increasing and see how much more dramatically response times goes up. On the other hand, looking at SSD2, the lower performance, higher capacity, again, we see much lower megabytes per second, 38 to 590. And again, the response time, quality of service, red bars all exceed the 1 millisecond. And at the end, we go up to 39 and 50 milliseconds when we are fully saturated. And then finally, looking at the next slide, which is a TCP case where there's no offload, we see on the left-hand side, SSD1, 68 to 2900. So the megabytes are lower than the previous SSD1 for the RDMA-based transports. Again, the response times start to exceed the 1 millisecond at 144 OIO, but much more. So instead of going up to 4 milliseconds or 5 milliseconds, we're going to 31960. So there's a very big difference here using TCP on the high-performance storage, that when you get to a high demand intensity, your quality of service response times get very, very high. So here, clearly the knee is at OIO 72 to 80, where you have 2800 megabytes per second and a 1.2 or 1.3 response time. Looking at the same on SSD2, again, the megabytes per second are much lower, 10 times lower. So from 2900, you're only getting to 600. You still have the sawtooth, where you have dips at certain multiples of thread count, in this case 8, 16, 32, and 40. And you see that the red bars are consistently above the purple line, 1 millisecond response time ceiling. And when you get out to the right, again, you're seeing the same 37 to 50 millisecond response time. So in the previous slides, you saw RDMA staying at 4 to 5 seconds, but for TCP going up to 60. And for SSD2, it didn't really matter. All the megabytes per second were low 600s, and the high response times were in 50 milliseconds. Why are these response times different? Well, you'd have to go and look under the hood. It could be anywhere along the chain from the storage to the host, but we have normalized the test situation such that we're only looking at the IOs going across the wire at whatever frame rate and testing the logical storage on the target side. Again, the only variables being changed are the frame size and the transport protocol. So, in conclusion, for CPU, we see pretty low CPU utilization on the target storage, 1% for RDMA and 4% for TCP. It looks like a low number, but if we really isolate on that, we can probably get more accurate readings. For the frame size, there doesn't appear to be much difference between the standard and jumbo frames, although certain small block sizes for the jumbo frame have very poor response times. Comparing the two types of SSD, the high performance, low capacity SSD1 has significantly higher IOPs and lower quality of service response times than the lower performance, higher capacity SSD2. But again, SSD2 shows higher performance for those certain small block sizes and certain sequential 128K reads. Again, I want to emphasize that this is a first pass testing and we need to validate the findings and look into those anomalous or high readings and see what's causing them and perhaps optimize the setup to evaluate what's really going on. From the thread count QDEP sweep, we saw that as we turn up the band intensity, IOPs and megabytes per second increase, but the quality of service, figure of merit, peaks, and you can see that the response time cost for going up is quite significant. And one note is this real-world workload happened to be 100% write workload, and we have a variety of other workloads we can look at, and we intend to look at a 6535 or a 6832 read-write workload in the next run. As far as the transport, the RDMA are substantially similar and faster than TCP. They have similar optimal outstanding I/O test points. Saturation occurs between 288 and 576 using that real-world workload, which has 9 I/O streams, and that value can change depending on what kind of workload you use. And we also see RDMA has lower response times than TCP. And finally, between iWARP and RoCE, we see that RoCE has a little bit better response times than iWARP. So Fred is back, and I'm glad you couldn't hear what I did to your slides, but maybe I'll hand it off to you very quickly if you want to recap anything.
No, I think you did a great job. Present the data. We did a lot of tests with different scenarios. This is a great summary of what we've done.
Okay, so Tom, I guess we're at the question and answer session. If anybody's still awake out there.
Right. We have a number of questions folks have typed into the windows for us. And let's begin with some of those that I marked as far more interesting. Of course, if your question doesn't get answered now, it will be in our blog later, so please don't feel disheartened about that. Fred, what are the specific characteristics of RoCEv2 that restrict it to a rack scale deployment? In other words, what is restricting it from larger scale deployments?
If we go back to the slide in section 1, you can see RoCE is built upon UDP, and iWARP is built upon TCP, and of course TCP transport has its TCP flow control and the congestion measurement mechanism. So this is the unique characteristic for RoCE for the scalability. We're not saying RoCE is not scalable, but when we scale to more nodes, there are more challenges for any of the protocol built upon UDP transport layer.
No, that makes sense. Sure.
Yeah.
And another question for either of you. Given that NVMe SSD performance are high with low latency, is it not that the performance bottleneck is shifted to the storage controller?
So I can take this. So basically, as I said, we're pushing IOs over the wire to the logical storage. So the storage controller is at a layer below the logical storage that's identified. So the short answer is yes, the storage controller can be the bottleneck, as well as anything else between the storage and the NIC card. If you look at storage testing without going across the wire, then we could eliminate that layer and look more directly at controller level to controller level, and then all the other hosted issues involved, which have to do with garbage collection tables and caches and so on and so forth. But again, we've normalized or tried to normalize everything on either side of the NIC card, so we can just see the effect of frame size and transport going across the wire from the host to the target.
Okay. Similar. some details about the SSDs and how they're organized. Are the six SSDs on a single namespace or separate?
We actually use a single name. Yeah, we actually use a single namespace. It's a single
Okay. That makes most sense. What factors will affect the performance of NVMe over RoCEv2 and TCP when the network between host and target is longer than a typical data center environment? That is, when you've got a round-trip time of better than 100 milliseconds.
I can take a shot. It's a good question. In this presentation, we're purely focusing on the host side factors. That's why the test setup actually was back-to-back without switch sitting in the middle. But in the future, we do plan to have a switch scenario so that we can look at the performance along the network paths and take into account the switch impact. But overall, I think the scalability of the NVMe over Fabric solution and also the performance in a large-scale network deployment will very much depending on all those factors along the line, not only the switch, but also the endpoint and also the workload running on top. So it's a combination of multiple factors, and what we're doing here is trying to isolate each factors one by one and see how each one would impact the performance and impact the performance in different ways.
Sure. And in a similar vein, we have another question about, was the RoCEv2 tests run on a lossless Ethernet and the TCP tests run on a lossy Ethernet?
So it's a good question here. Again, we do not have a switch in the middle, but for all the tests that we've done in this presentation, we turn on the link flow control, which means we provide the quality of service on the network for all the transport.
Right. And Eden, do you know if we're keeping track at all of number of lost packets?
No, I don't know.
We're just assuming that it's basically perfect or lossless.
I'm not saying that. I'm just saying I'm the mindless scribe without expertise in that domain. I leave it to someone else to answer.
Okay.
Got to know what you don't know.
At least in this test, I don't think we are setting up any counter to look at the number of packets that lost in the test. But that could be a very good, performance indicator that we can put into a future test. But in this test, we didn't put any performance counter that monitor the number of packet lost.
Sure. Yeah. No, that would be another good thing to add for real-world simulations.
Yep.
Sure.
Good point.
And somebody asks, is this pure RoCEv2, like no TCP? And that is true. It is RoCE/UDP from end to end, and that's it. There's nothing else in between. There's a question about preconditioning. Could you cover that briefly for us, Eden?
Sure. So the question is, how are drives being preconditioned? Is it based on IO size or MTU size? It doesn't have anything to do with the MTU size. The IOs that go across the wire are applied to the storage, and those block sizes and read-write mixes are based on the workloads being used to precondition. So we run the workload, whether it's a corner case or a benign IO stream workload, to the storage until it reaches steady state. So for the case of the ThreadCam QDEP test, we run that 9IO stream until it stabilizes, and then when we change the when we change the outstanding IO from 1 to 576, we run that loop continuously and take the values over repetitive loops to see that it's stable. So long story short, we're using the workload to preconditioned storage, and then we test it once it's stabilized into a performance range that doesn't change over time, or is relatively time invariant.
Okay. We've reached pretty much the end, and very shortly we're going to get cut off by our host here. So we can go all the way to the very end.
Yeah, I just want to highlight for the questions not answered in this presentation, we'll use blog to answer all the questions. We'll capture all the questions after the presentation. We'll answer them with our blog.
Right. So here's the link to the blog. It's in the slides, of course, so if you don't get it now, again, please rate this webcast and give us your feedback. It's the only way we know whether we've done anything right and what can we do to make it better. Thank you all so much for your time and attention and your questions. We will get back to you with this one. Thank you again.
Thank you, everyone.